Hello and welcome to this video. I said in my last video that we will study binary trees and so on. So this is basically the beginning of that kind of videos on algorithms and data structure which involve searching. So this you can think of this as a prequel to binary search trees or red-black trees or AVL trees. The main benefit of binary trees is search, or for that matter, things like suffix trees or tries and so on. The main concern is search. So to begin with searching, we will take linear search as an example, which is one of the most rudimentary problems. So we have an array of numbers which is unsorted, and we are going to perform linear search on this. So clearly the complexity is big O(n) in this case. We have the header file which has the function linear search, and in the implementation file we take an element and we iterate over the entire array, and if it matches we print that it is found at this location and then we return. Otherwise we print given element not found. So it is pretty straightforward. Let's see this in action. So I will invoke GCC on this and let me call linear search. So we run this, we want to search 705. It is found at the third location. Now O of n is not very interesting complexity because it scales linearly with the size of data. So the more data means more time taken in a linear fashion. So it is not very useful. So the question is, can we do better? And the answer is yes. But there is a precondition of this answer, that if the array is sorted, then we can definitely do better. Now remember that sorting an array takes typically n log n. Okay, when you perform something like quicksort, it typically takes n log n. But if it is one-time operation if the array is fixed. If the array is sorted, we can perform binary search. So what we do in binary search is we find the middle element, and if the middle element is less than the element to be searched, then we go to the right side. Okay, and then we find the middle element of the right half, and then accordingly we go to left half, right half, all the time bringing down the size of array by a factor of 1/2. So that means if you do the preliminary mathematics, you'll find that in log of n with base 2 number of steps, you will arrive at the result. So the header is simply prototype declaration of binary search, and the implementation is pretty simple. We take the elements to be found, we find the middle element. Now note that I have not said first plus last by 2 in this case to find middle element, because if we do that, there is a chance of overflow. So that might not give you correct middle element. So we have found the middle, and this algorithm works in such a way that if the element is not found, then first will become greater than last, because we make first is equal to middle plus 1. Okay, so if the element wouldn't be found, it will become greater than last element. Now if the middle element is equal to search, then we say that we have found this. Otherwise we make first is equal to middle plus 1, else we make if that is a middle less than search. All right, then we go to the second half. Otherwise we go to the first half by making last is equal to middle minus 1. And after all this, this is a mistake here. This shouldn't be first plus last. This should be first plus last minus first by 2. Okay, so that's the whole algorithm, and let's see, by compiling this is the iterative implementation of binary search. So we call GCC again, We do a binary search on the same element. So this time it is found at location 7 because the array is sorted. Now let's try to find out some other element. Let's look for 890. 890. So it is found at location 9. Let's try to find 211. 211. So it is found at location 2. We try to find 164. 164. Yeah, so it is found at the location 1. Now this recur binary search is recursive implementation. In this case, we also supply the element to be searched in the function call. So the header is again simple prototype and the implementation is more or less same. So in this case, we compute middle, we do the same first greater than last, and we perform the same logic. And if we have found, then we return, otherwise we recurse with new first and new last. So that's it for this video. In the next video, we will start by binary search implementation. The motivation of binary search, binary tree implementation is that we do not want to make the array sorted, in the sense that sorting requires n log n time. So we want a data structure such that if we insert an element, it automatically forms a structure such that it is suitable for searching, that it gives us log n base 2 time for searching. So we'll see how we achieve that by doing binary tree. And then there are properties like self-balancing trees. So we'll see that how self-balancing trees come into picture by doing an implementation of red-black tree. And we will know why balanced binary trees are important. So with that, I will leave you. And if you have liked this video, then please subscribe to the channel and hit the like button. You might also want to switch on the notification by clicking the bell icon. So if you have a question or you comment or you want to say something, then please make use of the comment box. I'll see you in the next video. Happy programming.